So let's get started on working through the electric field of a ring. So I mentioned that you should look through it at least before you come to class today. So we'll start on it. So I'll draw a ring like that, and this is on the XY axis. So we can say this is X and that is Y. And we'll take a certain point on this ring, or a certain segment of the ring like that. This segment will have a charge dq, and we can say that it has a length ds. And I'll tell you shortly why I'm using ds. Okay. The ring has a radius r, and we can say the angle here of this segment is phi. Okay, so we can say that that segment of length ds will have that length ds can be written as r times d phi. So this just comes from the length of a segment of the circle. So if you have a circle like that, and you just take a segment s of that circle of angle phi and radius r, then s is equal to r phi. So we can say ds is equal to r d phi. Okay, so that's what I've done. So we assume that that ring is uniformly charged with total charge q. Total charge is q, and we shall say that charge density is lambda. And we're just using the charge density for a line because a ring is basically just a line. So we're saying the charge density is lambda. So this segment here will produce an electric field at that point in space, which would be the electric field d subscript e. So the angle here is theta. So with this, we shall have a component of the electric field, which is the dE y component, and then we shall have an x component, dEx, like that. So we have two components for the electric field, and so this angle is theta also. Is everybody seeing that? So we know already that the electric field dE is k dq over r squared, where this is r, and we have the radius, and this length we can call y because it's on the y-axis. So the electric field E can be written as an integral of k dq over r squared, where we are going to say that r squared is equal to y squared plus r squared. Our x component of the electric field dEx is equal to dE sine theta, and our y component dEy is going to be dE cosine theta. So the x component of the electric field disappears by symmetry. So the x component of the electric field cancels. And so the only component of the electric field that we shall have left is the y component, which is equal to dE cosine theta. Therefore, the y component of the electric field, which is pointing straight up, is just dE cosine theta. And we already know dE. We said dE is k dq over r squared, so we put that in there. And we know that dq is equal to r d theta. So let's use that also. So we're going to integrate from 0 to 2 pi k times r d theta divided by r squared plus r squared, which is y squared, plus r squared. And cosine theta is going to be, so we'll put cosine theta here. Okay. And then we'll go back and look at cosine theta. If you look at the way it's set up, cosine theta is going to be adjacent over hypotenuse, so it's y over r. So cosine theta is equal to y over r, where r is going to be just y squared plus r squared raised to the power half. So it's the square root of y squared plus r squared. So Ey can be written as the integral from 0 to 2 pi k r d theta, and there's a y there, divided by y squared plus r squared raised to the power 3 over 2. So I've basically just combined y squared plus r squared, and I've multiplied it by y squared plus r squared raised to the power half. Okay, so that gives us the y squared plus r squared raised to the power 3 over 2. So we can now take, since if you look at this, we are only integrating over the angle theta. Actually, let me see what I'm integrating over. In this case, I'm integrating over y over phi, sorry, not theta. Okay, this angle here is r d, the length of the segment is r d phi. So this dq, if you use the, so let me make that correction first. I'm integrating over phi, not theta. So this is integration over phi, phi, and phi, because those are two different angles. And the reason I'm getting it that way is because I had the charge density, which is just going to be equal to the charge per unit length ds. So dq is equal to lambda ds, and ds is r d phi. So this is dq. So I'm replacing that in there. So when I replace dq by r d phi, I should have a lambda in here. And so there's a lambda right there. So that should clarify it now. So we are integrating over the angle phi, so we can take everything else out of the integral sign. So we can say lambda, k, r, and y all come out. We can remove y squared plus r squared raised to the power 3 over 2. And we just left with an integral over 2 pi d phi. So the y component is given by lambda times k, and then since we're integrating about 2 over phi, it's just 2 pi, and multiply that by r, and there's a y there, and then we take out our y squared plus r squared raised to the power 3 over 2. So basically this is it, we are done with it. So the next thing is we need to note that since the ring has a total charge q, then we can say that lambda, which is a charge density, is the total charge per unit length. The ring has a length which is the circumference of the ring. What is the circumference of the ring? What is it? 2 what? Yeah, 2 pi r. So the ring has circumference 2 pi r. So the total charge density is the charge per unit length, which is total charge q over length 2 pi r. So we can replace that in that formula there, and we shall have lambda, which is q over 2 pi r. So we shall have k times q, and then we have 2 pi r times y, and divide that by 2 pi r, and then we have y squared plus r squared raised to 3 over 2. So we can take the 2 pi r's out like that, and we shall have q times y. And if you want to use 1 over 4 pi epsilon naught for k, then we can write 4 pi epsilon naught. We have y squared plus r squared raised to the power 3 over 2. Okay.
What happened to k?
The k is 1 over 4 pi epsilon naught. Okay, so I'll put here that k equals 1 over 4 pi epsilon naught. So this is the electric field in the y direction for an electric field along the y-axis for a ring, as I set it up. In your textbook, they put it along z, so the only difference is you replace your y's by z and you get the same result. So everything is the same, except that instead of y in your textbook, it's z. So if you see y, you just replace by z, so it gives you the same result. Any questions on that? Okay, so let's continue. So that's the electric field of a ring. We can look at the electric field of the disk next. Okay, so we can consider a disk of radius r and uniformly charged with a total charge q. So we can let's find the electric field at an axis perpendicular to the let's find the electric field along the y-axis. So I'll set it up along y. So this is the disk again. This looks just like a ring, of course, but it's set up a little bit differently. So this is the disk. The radius of the disk is r, and we are going to take an element which is a small ring in the disk. Okay, so we'll take that ring in the disk. Let me redraw this. This doesn't look very good. So we'll draw a bigger disk. So the disk is along the y-axis, and we're taking a ring in the disk. So we'll break the disk up into small rings like that. The disk has a total radius r, and this ring has an element. The ring has a thickness dr. So we take a thickness of the ring dr like that. It subtends an angle here. Okay, and this will be a radius lowercase r. So we can say the disk has a total charge Q. So the charge density on the disk is sigma. Remember, we used sigma last time for the charge density for a disk, I believe. Let's see. Oh, surface. No, we used eta for surface charge density. Sorry. Let me change that to eta. So in your textbook, the charge density they use is eta, like that. And that charge density is the total charge per unit area. So we'll say that since it's uniformly charged, eta is equal to dq dA, where we shall take A to be the area of the strip. So we take that little ring there and stretch it out into a strip. The ring will have a thickness dr, and this is 2 pi r is the length of the strip. The thickness is dr. So the surface area dA, which is the area of the strip, dA is equal to 2 pi r dr, like that. So what I'm doing is I'm taking this segment to have a charge dq, and I'm saying that it's going to produce an electric field at some point in space dE, and then I'll do the same thing again. I'll take the angle here to be theta, take a component there and a component there, and then this angle that I have here is phi again, just like we had before. I'll take this angle to be phi. So when I integrate that, it gives me the 2 pi already. So I think that area is already taking that into account. So dq is equal to eta dA, which can be written as eta times 2 pi r dr. So that is our dq that we shall use in our integral. So our electric field dE along the y-axis is dE cosine theta again, and dE along the x-axis is equal to dE sine theta. So the x-axis is this component here, and this is the y-axis again. So x is dE sine theta, y is dE cosine theta. And what about sine the x component? Is that going to what would that give us? The x component. If you look at the symmetry of it, what happens to the x component? Yeah, by the symmetry, the x component will cancel because there's going to be another x component right here. Do you see the little dot there moving on the next word? There's going to be another x component right here. You see that? So that will cancel the other x component. So the x components go away. So we're just going to be left with a y component for the electric field, which is going to be dE cosine theta. So by symmetry, the x component of the electric field cancels. So we are now left with the y component only. So we are only left with the y component of the electric field. So dEy is dE cosine theta. So the electric field in the y direction is just the integral of dE cosine theta, where dE can be written as k, and then we have dq, which is eta. So dq is eta 2 pi r dr over r squared, and so we'll put that in and then do cosine theta. So we have k eta 2 pi r dr divided by r squared, where r squared is again going to be just given by y squared plus r squared. And then we have cosine theta, where cosine theta is going to be adjacent over hypotenuse, and hypotenuse is again r squared plus y squared. So y over y squared plus r squared, like that, raised to the power half. And let me make sure that I get the right notations for you. Okay, so I'm using r down here for the radius. So let me use, let's see, let's use r prime here so we don't get it mixed up. So this is basically r prime squared. So this is r prime squared. So the r prime is just the square root of y squared plus r squared, because I'm going to be integrating over the radius r. So I'm integrating from 0 to r, where r is the radius of the disk. So EY is an integral from 0 to r. So since I'm only integrating over r, I'm going to take some of the things out of the integral sign. I'll take k out, take eta out, take 2 pi, and then I'm going to have the integral from 0 to r dr, and divide that by y squared plus r squared, and raise that to the power 3 over 2, because I've now put in cosine theta. Cosine theta is y over y squared plus r squared. Is everybody seeing that?
So shouldn't there be a square on the one above it? On the y squared plus r squared?
Here, this one, that is raised to the power 1 because it's r prime squared. Yeah, it's raised to the power 1. So that's why I can do it the way I'm doing. So this is raised to the power 1.
Yeah.
And the other one is half. So half plus 1 is 3 over 2. So what I want to make sure is that you are following me when I say that this section, this is r prime, not r. You see, the notation, I'm using two of the same notation. I'm going to be integrating over this r here, because this is a ring. I'm going to take segments of this ring and integrate all over from here to here. So I'm integrating over r dr, and so this here is r prime, which is where the electric field dE is going to be k dq over r prime squared for the distance from here to there. So I'm using r prime for that. Normally we've been using r, but because I'm going to be integrating over r, that's why I'm using r prime. So that's where that comes in. This one here is r prime, that as I wrote before. Let me write it better so you can see it. R. So let's write it this way: r prime squared, so that you can, so it's clear. Okay, and the r prime is therefore that is the hypotenuse of that triangle. So it's y squared plus r squared. So r prime squared is y squared plus r squared. So everything is now consistent. So the only thing left is to do this integral from 0 to r dr over y squared plus r squared. So again, for this situation, there's an integral table in the back of the book. So we just use the integral table. So on this integral table, so x, so it's going to be minus 1 over square root of x squared plus, in this case, square root of y squared plus r squared. So the integral of r dr over y squared plus r squared raised to the power 3 over 2 is equal to minus 1 over the square root of y squared plus r squared, according to the book. So this is from table. I'm sure you can do it in using the calculus form, but in physics we just usually look at the table and we get that integral out.
What page did you say the table is on?
The table is, let's see, the table is in the appendix A3. This is appendix A3. So we can use that. So the electric field in the y direction, we'll just write it as k, and we'll change the k later on. But let's put this here. So we have y already out there. So we have ky times 2 pi, and then we have minus 1 over the square root of y squared plus r squared, 0 to r.
When you moved 1 over y squared plus r squared, it doesn't become a positive?
Say that again?
I mean, if you moved it over the equal sign, wouldn't it become just a positive value?
If you move it to the equal sign?
You moved it across the equal sign.
No, I didn't move it across. This is, I'm just solving the integral here. So I'm just using this formula to solve this integral. So all I've done is I've just solved it now, and so that's why I put it this way. So all we have to do is to say k.
Oh, okay.
Yeah, ky times 2 pi, and then you're going to take the first one, 1 over the square root of y squared plus r squared minus, and minus makes plus. There's going to be 1 over the square root of y squared plus 0. Okay, so that's what I wanted you to do. So now we shall say Ey is equal to k times y times 2 pi, and then I'll rewrite it as 1 over y minus 1 over the square root of y squared plus r squared. That way. And we have a y outside, so we can multiply through by that y to see what happens. So we have the electric field Ey is equal to 2 pi, and then there's a k. If you like, we can make the k 4 pi epsilon naught. I think I've lost eta somewhere. Did I lose eta? Yes, I did lose eta. So there's an eta in here somewhere. We don't want to lose our eta. So this is 2 pi. There's an eta here like that. And then when you multiply through by y, you have 1 minus y over the square root of y squared plus r squared. So from here, I'm going to take out a pi, take out one of the 2's, and I'll have Ey equals eta. This is eta over 2 epsilon naught, and then we shall have 1 minus y over the square root of y squared plus r squared. Let me rewrite this eta. It looks a bit like a y. So this is eta like that. So this formula is going to be important for us when we get to the parallel plate capacitor. So that's why I wanted to do it, so that we know how to what the electric field of a disk looks like. Okay, so let's look at what happens when we look very far away from the electric field. So suppose we want the electric field at some point far from the disk. And what we'll do is at some point far from the disk, we're going to say that the electric field, we're going to say that y is much, much later than r. Or we can say y approaches infinity. So if y gets very large, then y is much, much greater than r. So at some distance very far away from the disk, we can find what the electric field looks like. So we say that at some point far away, y approaches infinity. We can rewrite y over the square root of y squared plus r squared as follows. So we can say this is y square root of 1 plus r squared over y squared, and then the y squared comes out, so I think the top part becomes 1. So this becomes 1 over y. Do you all see how that works? So we want to write it in a way so that we can use the approximation that this is since this is much, much larger than that, this is approaching infinity. So we want to rewrite it in a way which will allow us to factor out this quantity here. Okay. So what I've done is I've just divided through by y squared. That's why I have r squared over y squared here. Now if I take out the y squared at the bottom here, then I can just remove it. So it's basically like I'm taking out a y squared. I'm dividing it through by y squared, so I need to put the y at the top, because once this y enters the square root, it becomes y squared. You realize that? If I take a y squared out, it becomes a y. If I put y squared, if I put a y in, it becomes a y squared. So if I put this y in, it becomes y squared plus r squared over y squared, which gives us a result. So that's why I put a y out there. So that will cancel the y on top. Does that make sense to everybody? So this y will cancel that y there, and so that formula there becomes 1 over the square root of 1 plus r squared over y squared. And this r squared over y squared is less than 1. So we're saying r squared over y squared is x. Okay, so let me say that this way. R squared over y squared x, so x is less than 1 because the y approaches infinity. And so we'll do that, and then we'll say that this is 1 over the square root of 1 plus x, like that. So 1 over 1 plus x raised to the power half. That's how you write it. So this allows us to use the binomial approximation. So binomial approximation says that for x less than 1, 1 plus x raised to the power n is equal to 1 plus nx. So if we have 1 plus x raised to the power minus half, this is going to be 1 minus half x, like that. So that means that we can write x, which is r squared over y squared. So we shall have 1 minus half, and then we have r squared over y squared for the binomial approximation. So this is the same, okay, where x is equal to r squared over y squared. So this means that our electric field at distances very far away can be written as eta over 2 epsilon naught, and then we shall have 1 over the square root of 1 plus r squared over y squared, that way. So E can be written as eta over 2 epsilon naught, and we have 1, and then we shall have in parentheses 1 minus half r squared over y squared, that way. Well, we can put another one there like that. All right, so I believe we are getting to that point. So let's write it out. So E equals eta over 2 epsilon naught. The ones cancel, so we shall have a half, and then we shall have this quantity here, r squared over y squared, like that. And so this becomes eta is q over 2. Eta is q over the surface area pi r squared. So we can write it this way. So we have eta. So eta is q over 2 pi r squared epsilon naught. The extra 2 is there, so we have a 2. And this r is just the radius of the disk, so let's put it as r squared. We have an r squared here divided by y squared. So this becomes q, the r squared cancels out, divided by 4 pi epsilon naught y squared. So this is basically just the same as the electric field of a point at some distance away. Any questions on that?
Was the 2 was with the r squared y squared, right? Not under
the 2 were
between epsilon naught and y squared.
That 2 multiplies by this 2 to make it a 4. So at this point here, the 2 epsilon naught is a 2 here, so I made that eta is q over pi r squared because the surface area of the disk is pi r squared, where r is the radius. Okay, so q, the eta is equal to the charge density. So let me show you where that comes from. So this is your disk. The disk has radius r, total charge is q, so the charge density is charge per unit area, which is q over pi r squared, like that. Okay, so that's where that comes from. So I just replaced the eta by q over pi r squared, and I cancel this r squared with that r squared. This 2 multiplied to give you 4 pi epsilon naught. Your y squared is still there, and q is there. So this is just the electric field of a point. It's just the electric field of a point charge. So I wanted to do this because now we're going to get into a plane of charge and parallel plate capacitor. So let's continue with that before I close this up. So we'll go to the next one. So we can say the electric field of a disk. Okay, so we are going to assume, let's say that we want to find the electric field of a plane, and we are assuming that the plane is infinitely large. So we shall use our result above. So our result is that the electric field of a charged disk is equal to eta over 2 epsilon naught. And then what did we have? Eta over 2 epsilon naught 1 minus, let me take it from here. Eta over 2 epsilon naught 1 minus y over square root of y plus y squared r squared. So this was our original electric field for a plane of for a disk of charge. So if we wanted to find the electric field of a plane, we can make the approximation that suppose the plane is infinitely large so that the field is spread uniformly over the surface of the plane. Okay, so we can say that suppose we have an infinite plane so that the electric field then is going to be uniform on the plane. So we're not worried about the edges of the plane. So we're going to say that R is much larger. So let's say R approaches infinity, or we can say R is much greater than Y in this case. This is opposite of what we just did where Y was greater than R. Now we are saying R is greater than Y. In this case, we will say that in this case, Y over the square root of Y squared plus R squared, square root of that, is going to approach 0 because R is much larger than everything in there. So this should approach 0. So we can easily now say that the electric field of an infinite plane of charge, where this is our charge density eta, and this is 2 epsilon naught. So we have 1 minus 0. So the electric field of the plane of charge is equal to eta over 2 epsilon naught. And so this shows us that the electric field is a constant for a plane of charge. It doesn't depend, as you can see, on the radius of the disk or the distance from the disk. The electric field for an infinite plane is a constant quantity. So this will be true for a plane like that, charged plane. Suppose we have positive charges all over this plane. Then the field is just going to be perpendicular to the plane. At everywhere along the plane, the field is perpendicular. And then the field is also on the other side of the plane. So this is the field. So we can say the electric field for the disk can be written as eta over 2 epsilon naught above the plane. Suppose the plane is on the xy axis. This is equal to eta over 2 epsilon naught for y greater than 0, or minus eta over 2 epsilon naught for y less than 0. Suppose that actually not y but z. I'm putting it on the xy plane. So this is z. So this is like that, z, and then we have something like this, x over y. Okay, so this is on the xy plane. So so the electric field is up and down along the z-axis. Okay, so eta over 2 epsilon naught for z greater than 0 and minus for z less than 0, like that. We'll work on the parallel plate capacitor next.